All right, welcome back to The Explainer. As the chief architect of today's session, I am absolutely thrilled to welcome you to our high-rise exam construction workshop. Today, we're putting on our hard hats to tackle a famously tricky module, Cambridge Mathematics 9709. Specifically, we're zooming in on section 4.5. That is the exact, precise point where kinetic energy, potential energy, and work done all collide. Now, to help us understand how to engineer those top-scoring answers, I want to introduce you to two of our apprentice builders. First up, we have Alex. Now, Alex has this habit of stacking up unorganized factual bricks, basically just dumping equations onto the page without any mortar to hold them together. And then, on the other hand, there's Sam. Sam focuses entirely on the flashy final answers, completely ignoring the load-bearing working steps you actually need to hold the whole structure up. And let me tell you, neither of these approaches is going to survive the scrutiny of Cambridge examiners. So today, we are going to fix that.
Here is our blueprint for today. 1. The trap. 2. Examiner warnings. 3. The standardized sequence. 4. Method marks. And 5. Higher order strategies.
So, we really have to ask ourselves, why do so many students find multi-stage analysis and those crucial method marks in the 4.5 energy module so incredibly hard to secure? Well, we're going to examine the core mark-dropping trap right now. Look, the Cambridge syllabus explicitly states that top-performing candidates exhibit connected, conceptual understanding that is totally transferable to unfamiliar contexts. The trap here is that students, like our builder Alex, will memorize a formula, say equating E equals mgh to E equals 1/2 mv squared. But then they completely fail to apply it when the context isn't perfectly identical to their textbook. They treat the problem as a set of isolated blocks rather than what it actually is, an interconnected physical system.
Section 1. Stress testing the framework. Let's look at the assessment objectives.
As Alex and Sam map out their structural skeleton on our digital grid, you can really see that the assessment framework requires highly logical reasoning. It's all about balancing knowledge, application, and analysis. The source material is crystal clear on this. Examiners prioritize analytical depth way over superficial breadth. You can't just write down every single mechanical energy equation you remember and just cross your fingers hoping one sticks. No way. You absolutely must show exactly how the initial mechanical energy, maybe starting entirely as gravitational potential, transforms into kinetic energy, or maybe how it's lost as work done against friction, and you have to do it step by step by step.
So the crucial takeaway here is avoiding these three massive structural failures, and we pulled these straight from the Cambridge Principal Examiner reports. Number 1, students forget to include the proper format, which means immediately losing easy marks. Number 2, they fail to check their presentation. Think about it. If an examiner can't follow your logic, they literally cannot reward it. And number 3, answers are not specific to the context given. If the question involves a particle moving up a rough inclined plane, your energy conservation equation has to specifically account for the work done against friction in that exact scenario. Generic answers are basically like weak concrete. They're just going to crack right under pressure.
Section 2. Reinforcing the pillars. Time to build the standardized sequence.
Hold up, site inspection. Before we weld our evidence to our analysis, I need everyone watching to fortify your academic foundations. Subscribe to Ace the Exams at the handle @AceTheExams right now to get weekly structural grade upgrades. Okay, inspection complete. Now, when our builders hit an unexpected structural crack, we immediately deploy this 5-step procedural framework. First, you identify the key elements, what forces are actually acting here. Second, apply the relevant principles, like energy conservation. Third, execute your analysis with abundantly clear working. Fourth, verify your results. And finally, present it in the appropriate format. This right here is exactly how you build an unshakable argument.
Listen closely, because this is your ultimate safety net. If your final calculation crumbles, load-bearing method marks will rescue your grade. This is a direct alert straight from the examiners regarding the 4.5 energy module. You remember our builder Sam? Sam loves to just skip right to the flashy final answer. But if Sam makes one tiny little calculator error, the whole structure scores a big fat 0. You have to show you're working. Write out the kinetic and potential energy components fully before you even think about simplifying. Those method marks, they are literally the steel rebar keeping your final grade intact.
Moving right along to Section 3, Interactive Viewer Stress Test. Let's run some live audience diagnostics.
All right, I want you to set your 60-second mental countdown timers for Test 1. You need to demonstrate top-tier evaluative thinking by extracting data, interpreting physical relationships, and drawing solid, evidence-based conclusions. Look, if a question gives you the mass of an object, the distance it falls, and its final velocity, top-scoring candidates don't just blindly plug numbers in. They evaluate. They explicitly state, assuming air resistance is negligible, the change in potential energy equals the kinetic energy. Identifying and writing out those baseline assumptions is exactly what elevates your answer to the absolute highest tier.
Okay, for test 2, identify the flaw. I really want you to notice how the lower tier descriptive answer causes a complete mark drop when you compare it to the high-scoring evaluative framework. A descriptive approach simply states energy is conserved. Cool, that's just a basic physics fact. But the evaluative approach, which by the way is exactly what those higher order assessment objectives demand, requires you to justify your decisions with actual evidence. It looks more like this. Because only conservative forces are doing work on the system, mechanical energy is conserved, allowing us to equate the initial mechanical energy at point A to point B. Do you see the difference there? One is a loose brick tumbling down, the other is a bolted steel beam. Section 4. The final build inspection. Let's check those strict conventions.
A flawless exterior finish requires strict, unwavering conventions. You need to define your variables, use standard SI units like joules, and annotate exactly when and where you apply the conservation principle. To lock in this methodical processing, try a memory hack using the first letters of our standardized sequence. Identify, apply, execute, verify, present. I personally love engineers always ensure very perfect structures. Using a mnemonic like I8 EVP in the exam hall grounds you. It ensures you never ever skip the load-bearing steps that builders like Sam so often forget.
So, as we wrap up today's explainer, I want to leave you with this final, somewhat provocative thought. Are your exam answers built to just collapse under pressure, or are they engineered to achieve those top marks? It is entirely up to the framework you choose to use. Don't be an Alex throwing unorganized facts around, and definitely don't be a Sam with flashy, completely unsupported final answers. Build systematically. Before our next masterclass, make absolutely sure to subscribe to Ace the Exams at the handle @AceTheExams, hit that notification bell, and leave a comment down below with your specific subject and level. Keep engineering those perfect answers, and I will see you on the next site visit.